Hello everyone, my name is Philip Huttner. If you haven't seen me in the last meeting end of November, I'm the Mike Plus and Rivers and Mike Shi business owner at DHI. And today I will guide you through a 60 minutes webinar how to build a simple Mike Shi with basic modules in order to produce recharge for a groundwater model or other purposes. Today I actually have no presentation at all. We will simply directly start with doing things. For those of you who have not joined the last meeting, you can still watch the recording. But to wrap up a little bit, you may remember, for those who've joined, that Mike Shi is a fully integrated catchment model, and it offers a quite flexible modular approach. So what you see if you would start a new Mike Shi model, such a GUI. And today I will go with you through at least the steps for implementing the overland flow module, since Mike Shi has a full 2D hydraulic model, the 1D unsaturated flow module, and the evapotranspiration. If you want to join the next meeting mid-end of January, you will learn also how to build up the saturated flow model, which is basically a full finite difference 3D groundwater model compared to free flow or mod flow. And probably in March or April, I will teach you also how to build up a Mike Plus river model, which then can be used here as the rivers and lakes module. So if you stay tuned till the end of this meeting for the next 45 minutes, I will show you how to get from here, from a GIS project with a focus area, to a full model, including these packages. I will show you all the steps now, step by step, and how to produce such a thing. This is a fully spatially and temporally varying raster. What you see here is the produced recharge to groundwater. I start here in September. You will see the light blue to purple values are positive recharge rates, while since we were in the end of summer, yellow to brown and red were negative recharge rates. And what you see here is pretty awesome, I think. It's really like where you can see how precipitation enters the soil and reaches the groundwater. You can very good see the river valleys where you have a low depth to groundwater and more dynamics, while you have more, let's say, hilly areas where the wetting front needs more time to percolate down from the topography to the saturated groundwater table. So let's start. Small comment. What I will show you today will be a quick run through. That means to really achieve a running model with a few steps, how to do the pre-processing. I tell you, majority of the work will be done in GIS. You can use the Esri products like the ArcMap I'm used to use here, the more up-to-date ArcPro or QGIS or any other solution. But majority of the pre-processing really happens in GIS, and it's very important that you follow the steps you can see here. For each step in the next couple of weeks, I will add way more explanations, smaller step-by-step guides, covering more special cases within our new online manual. And there you will see also small YouTube videos that cover also the other modules and so on. So whenever you have a question that is not addressed by such a webinar, feel free to use here the very effective search function to find any problem that you have. Okay, let's assume you are an engineering office, a consultant, and you want to offer for a project that is right now offered by a municipality or an authority. What you normally start is with a focus area. So in this case, we are here in North Rhine-Westphalia in Germany. You have a focus area. For example, here, it's an association of farmers, and they want to know how much water they have. Can we have more water? Could be a drinking water supplier. It could be a wetland renaturation study. But where you start as consultant or as researcher, a scientist, with a focus area. And if you are a good modeler, a professional one, you will not draw a model domain like this rectangular box. You will start looking at the natural hydrological boundary conditions, especially when you want to do a fully integrated model with Mike Shee that includes groundwater, surface water, 1D rivers, evapotranspiration, land use, and irrigation. You must think bigger. We at DHI, we call such a model domain then the so-called envelope domain, because it's the combination of the surface water catchment and the underground subsurface catchment. But how to define that? How to find that out? What you can see in this GIS project is all public available data. So you start with a topographic map in the background to know where you are, where the cities are. And then you, I guess, in most of the countries, you have data, for example, like the river system. Where are my rivers flowing? Then you know already, oh, here's my focus area. If I would make here a boundary, I would miss all the contributions here, this inflowing rivers. So you can directly start zooming out a little bit. Normally, you also can see here in gray the surface water catchments. They are already more reliable. If you would do only a 1D, 2D surface water modeling, it could be already sufficient to take these surface water catchments and merge them. So for example, this one, maybe this one, because this one is flowing in here. Here you obviously have a bigger separation of two bigger catchments. Of course, it makes also sense to have always a closer look to the DEM, the digital elevation model. I zoom out a little bit again. So what you normally do, you should start from very large scale kind of. And then probably if you have a DEM 25 meters from ASTA or any other global database, which you can also find in a few weeks on our new online manual, you would probably try to clip that already to a little bit smaller extent to make it more handy for you so that you can use it within your GIS project. So what I did, I have here a DEM 25 meters for whole Germany. I clipped it already here within the spatial analyst under extraction, extract by rectangle. There you can use the raster data and extract it by a very large, I would call it data collection mask. Like here. So then you have a smaller grid and you can more easily handle it. By the way, the first thing when you start a Mike Shee, or sorry, a GIS project in every software, you should really think about which coordinate system you want to use. This is crucial for the whole modeling project. And this is also very important for the following steps, because you will prepare a lot of input data and it should use all a consistent coordinate system. In this case, we use this one. I directly define that. And whenever you pull in data, you should take careful that you're also using the correct transformations. A rule of thumb is, from this drop-down, take one of the most upper ones, ideally NTV2. This is a global, let's say, globally agreed transformation method. Once you have clipped out this one, you should, as you see here, the 25 meter raw DEM had initially not the correct coordinate system. So I changed that one. In this case, you go under Data Management Tools, Raster, Project Raster. You pull in your raster. Say where you want to have it. And you choose the correct output coordinate system. In this case, this is this one. And click OK. It always takes a few seconds, so I will jump over these steps. When you've done that, I get the same resolution, but now I have the correct coordinate system. And you should do that with every data. Whenever you get data, you collect it yourself within your research project or within your clients, directly bring them into GIS and align in the coordinate systems. Once you've done that, you also see already the topography, right? The over-regional dynamics are, here's a subcatchment beginning. The southern part is flowing completely somewhere else. You don't need to take care for that. But there is also a big valley in here that also flows more or less across your focus area. In addition to the DEM, if available, it's also recommended to use the over-regional groundwater isolines. I zoom in again a little bit. I know it looks a little bit confusing, but you have areas, for example, here. I give it a different symbology so that I can visually directly see from where the groundwater is flowing within the isolines. For example, here I have the end of a surface water catchment that is defined by the topography, by the DEM1. But I have here groundwater leaving the area. So that means here you have different borders of the groundwater isoline. Here is the highest point. So groundwater from here is flowing towards here, here, and here. And it differs from the surface water catchment. And this is something you should try to consider within your modeling process. So what you normally do then, of course, you try to align a little bit with the surface water catchment, but then you really try to simulate or to derive your model domain. Within GIS, you can do this with the drawing and the polygon. Now I turn off DEM again. I make the isolines a little bit less colored. And what you can either follow with the model domain an isoline directly, then you need to set a boundary condition because water is flowing in there, or you follow perfectly perpendicular to the catchment. So in this case, I'm not interested in these rivers here, but in this part. So probably I will try to come to that line at some point, but I would like to have a separation already here. So I would probably start here perpendicular until I reach the highest point of the groundwater. Here the surface and the groundwater catchment match each other again. Here more or less. And you always try to run perpendicular more or less to the groundwater isolines. Here again, you see a higher point. Maybe turning off the colored ones again. Joining here the highest point. And now, to be sure, I turn on the river domain, the model domain that we actually derived for this project, because this data here is based on a real project. And you see here, the red line, again, follows the perpendicular area and actually crosses here a river. So what you do here now, we prioritize the underground catchment and follow this line again. And then along here, we have the main river receiving all our water. So we follow this line again. And now you see there were good reasons, because here is a surface water monitoring station. If you want to validate or calibrate also the flows that you simulate within your river later, you probably want to extend your model domain a little bit. So what I do, I select this initial polygon and extend it a little bit. Whoop. I jump now over these steps, not to lose time. In this case here, you can convert graphics to feature, to a shapefile. Assuming I did that already, I end up with this model domain. This is now a polygon shapefile. And what I would do then already now, we start with a blank model. And you will see then why. In order to start a blank model, you open a new Mike 0 session, because Mike Xi is based on this basic platform Mike 0. that looks like that. We create a new file. Here you see always all products from DHI that are based on Mic 0. Here we also have basic tools and a Mic 0 toolbox, which I need to use later with you. But I can also start here a new Mic G model. I copy the path from the top, wait until the file is created, should take only a few seconds, and then it's completely blank. And I save this model file. We at DHI, and I recommend to do you the same, we have a name convention. We always call the SHE file, the model file itself, model. That will help to automatize a lot of post-processing tools later on a lot. And then we go in here. Let's see what we want to use. I told you we don't want to use groundwater today. So it will turn off the whole data that is needed to implement this module. And since I said we have this very flexible modular approach, when I turn it off, it only asks me for a lower boundary condition for the unsaturated zone module. I will show you later. So we will do today the overland flow module finite difference, the unsaturated flow. Also here you have several options. We will go today directly for the most complex one because it leads to these nice recharge maps and is the most sophisticated approach. And then we can go to the model domain. You can define it via a DFS file, so this Mic native grid format, or you do it via a shapefile. I recommend you to go for the shapefile because that gives you the flexibility to change the model resolution and size throughout the whole project execution phase. That means if you want to run a coarser model in the very beginning to get a stable model, to go into the calibration more quickly, then you can upscale it a little bit and make it coarser. And later when you go into the so-called production runs, in the scenarios and in the forecast, then you would go for a finer resolution. So you select the shapefile. In this case, we are using meter. It can also deal with feet. And it's directly suggesting a resolution on NX and Y and cell size. In this case, I say, for the moment, I want to work with 50 meters resolution. Now I see the box that I start here is too coarse. You should also try to align a more even origin. That makes it easier later on to upscale and downscale different model versions. And then we make the box large enough. And then you can see already that with our cell resolution of 50 meters, we more or less can run it with 300 times 300 cells. And this is still good. I would not suggest to go more than 900 times 900. So whenever you get across this threshold and you want to run really a full 3D groundwater model, including 1D rivers, it takes a lot of time. So your resolution, your desired one, is somehow linked on your model domain and the performance, of course. Once I have defined my model domain, I'm able to create a data collection mask. In this case, I made it a little bit bigger. Normally it would be fine to do it only for the small model domain here. Turning off the groundwater isolines again. But since in this case, we wanted to simulate really the whole catchment, including the big river system, we also have a bigger model domain that is covering also the subcatchments here, because we, in this case, simulated them with a more simplified model approach in order to get an inflow discharge for the river system in here, which was required. So what you should do now, you should select a data collection mask, which you use for all the following pre-processing steps. And you should make the origin, again, rounded to even numbers. Ideally, you see it here, to thousands or 500s or 50, depending on your desired model resolution. And when you have such a data collection mask, you can at least start with the DEM. So what I have here is I have a shapefile for this rectangle. I have a DEM here. I clip it with this data collection mask, and then I can export it in DEM10 or DEM5 by, where is it here? Also a very helpful tool, raster processing resample. So let's assume I have exported already my DEM, and I want to use it as input as DEM10.1. I put it in here, say again where it should be, and then you can change here any number that you want. 10 times 10, 10, 50 times 50. Since it's describing an elevation, you should go for the bilinear approach, right? If it's a land use grid code that gives you a certain category, 1, 2, 3, 5, then you take nearest. If it's an elevation, like the bottom of your groundwater aquifer or the topography, you should go for the bilinear approach to have a continuous topography. So what I do now, I've done that. In order to be more quicker, I do it for the smaller data collection mask or everything. So I clip the raster again to this DEM. And then what you normally do, you work with geotiff data. But geotiff data cannot be read by mic. What it can convert is ASCII rasters. So what you should do then is you take the conversion tool, raster to ASCII, take that one, define the output, change the type to ASCII. You see I've produced it already here. And then it will produce an ASCII raster, which is readable also via the text editor. This is the one that I produced already some days ago. If I edit that with Notepad, it looks like that. Probably you have seen it already. So we have the columns and rows based on this data collection mask that I used for the clipping process. I have a nice, even, rounded to 50-meter X and Y corner. You can see the cell resolution. If you're working with QGIS, it could be that this line is missing and the mic tools will throw an error. So you probably should always, within every intermediate step, check the output yourself and maybe add this column. Once this column is added, you can go again to your mic platform, to your mic 0 session, new file, go to mic 0 and the mic 0 toolbox, which offers you a quite big palette of very powerful options to convert data. In this case, grid is meaning ASCII to mic. You open a new setup with a double click. Next, navigate to your ASCII file. Sometimes you have an issue with that your computer does not allow you to work on C. So it could be beneficial to create a temp folder under C. Then you have here your ASCII raster. Click open, next. You can choose the correct coordinate system, or you can use local coordinates. Sometimes it could prevent some issues later if you work with local coordinates, but then you really need to take care yourself for consistency across the coordinate systems. You click next, you define your output. The rest you can always leave as default. And then don't directly click finish, but click execute. And then it tells you, well done, the DEM is created. If you create these grids yourself from an ASCII file, what you always have to do, open it and check if the data looks plausible. Sometimes you have maybe a decimal point separator issue and you don't see data. That's why you should always review the data yourself in the ASCII format already. Before you can use it within mic, we'll show you something. You would now expect you can directly use the topography as input. We can change it here from uniform which is only helpful if you have a very simple concept model, to DFS2. Navigate to the DM, in this case, sorry, that's already the correct one. And you see it's complaining, no valid items. Mike software is sensitive to the so-called item type. Every DFS2 and every DFS0 can contain a certain item type. What does it mean? You can always open any DFS2 or DFS0 data with here, and then always what you need to do in the top, you click Edit Items, and you see this type is undefined because GIS does not know which type you need. In this case, we need an elevation or topography. And once this is done, you press again Save. Yeah, okay, I cannot save it right now because I have no connection to the license system. But I have the other one prepared already. Topography, sorry, the correct item type is topography. And then I can use it. And now we have already the topography. Way easier is the climate. You can use one single value for the whole area, constant, which does not make sense at all. You will do it at least as a time series. You have also the option to create sub-areas defined via a grid code, and say for subcatchment A, I take time series 1, for subcatchment B, I take time series 2. Or you make even a fully distributed grid, also possible. You saw it in the last webinar, which is based on radar data or satellite images. In this case, today, we go for the uniform approach using one time varying DFS0. DFS0 is simply the native time format. And I prepared here some datasets also. You will have to do it for the precipitation and the evapotranspiration. For the precipitation, I have one source data. I go to the GIS again. In this case, I prepared it already. You probably have to look up where you get stations. We have here a German weather service that is providing us with these. I zoom out a little bit. You see here one blue dot and the orange dots. Blue are the precipitation stations. Here is one, here is one. And obviously the closest ones are these two here. And this is the one with the ID 617. That's why you can see them here under source data. And the easiest way to create a DFS0 time series, you see it here. We have a date and we have a precipitation with daily resolution. So what I do within the GUI, I click create. And I can create an empty DFS0 time series. You can even save when it should start, when it should end. You directly can give it here a precipitation rate because you created it from Mike. The interval is 1 day. Then you create the file. If you click edit, you see here the file. I double check my data again. It starts in 1941 and ends 2022. So it has 29,219 time steps. And you can adapt here. I have to check it again. 29, 219. And then we can even make it in a different way. I simply copy the values and paste them into this DFS0. I see there are some missing values. So you have to clean them. I did that already. So you simply have to delete the value or set it to 0. And create such a DFS0 again. Oops, sorry. Yeah, this is the finished model. Okay. And we do the same. So you can link here the DFS0 you want to take. In this case, we took daily. Sorry, this one. And we do the same for the reference evapotranspiration. Normally, you should take here a reference evapotranspiration based on some climate service, a national or global one, or you derive it yourself. You would find information about that by March on this new online manual. We normally use here the Penman-Monteith GRASS reference evapotranspiration as input because it's aligning with this Food and Agriculture Organization FAO 56 guideline. How to calculate that yourself based on raw climate data like wind speed and air temperature you would find online. Then we go back to the GIS. Let me check if there's a question. Okay. We go back to GIS. So we have now topography and climate data we have successfully introduced into our model. I can now turn off a little bit the rivers so that we can see more. Focus area for the moment we don't need anymore. Climate data we can turn off. And the next thing would be the land use. Sounds complicated, but normally you get, based on satellite images, always pretty easy land use data, at least on a coarse scale. I clipped it here already a little bit around my data collection mask. In this case, I use here the public available Corine dataset. It's Corine land use data. It has a CLC code. It has an English name. And whenever you start in your country using MikeShe, then you probably start with a join table that you produce yourself. So what you can see here, if you download the data, you would find this data on the Corine server. But the columns behind that is based on our work that we derived over the years. How to do that? We work here simple with Excel tables. That means you try to paste the categories that are based from Corine into your Excel here, the CLC code. And then you give it a translation. You can use ChatGPT. That's quite easy. And what we did here at DHI, we defined 15 standardized land use codes that are relevant for our projects in normal. And then we assign them with a grid code. So we have here a kind of a lookup list. That means we have a serial, here it is. These are the basic categories that we have. So this is how we call it, because we need the land use for 3 purposes. One is to set up the vegetation and evapotranspiration module. Another one is to derive the Manning values, the Manning roughness for the 2D overland flow module. And we directly take the land use grid or the land use information to create a kind of ceiling in urban areas. That means normally you can differentiate between residential area, building, and streets and give them a value, this is 1 per second, that prevents too much infiltration into the soil. And you will produce higher direct runoff. This is, by the way, also, of course, a very important calibration parameter. And then we have, of course, the German terms and the English terms. And directly a label column, how I use it later in MikeShe. So what I do, I have here my Corine join table, which I prepared over the projects, over the time, over the years. So you have to do that yourself, but we are happy to share this approach. So as long as you have Corine data and the English term, you're able to directly do all the following steps. So what I do, I export this Excel sheet to a TXT file. You can see it here. It's tab separated. Then I go into the GIS. In this case, there is already the join. No, it's not here. Sorry. Okay, they are joined already. Imagine they are not yet joined, and you use this code. I join them here. You take the field on which you want to make the join possible. I take this text file, and you see now the columns here are added at the back. Once I've done that, we even have template symbologies for our purposes. So that means we can directly give it the categories that we want to differentiate. And we differentiate, as I said, normally by these 15 categories because they are relevant characteristic for evapotranspiration purposes. And once you are here, you can directly convert to raster. So that means, in this case, feature to raster. Oh, sorry, I use directly the clipped one so that my grids always align perfectly. You see it now. It's ending here at the black box at my data collection mask. Then I pull in the feature, decide which value field. In this case, I start with grid code because I want to create first the grid code raster. And I do the next two steps then also for the Manning value and for the subsurface grid. So I create two rasters, three TIFF rasters, which I then again convert from GIS to an ASCII raster, which I then convert finally to the MIC native format. Important, when you have created the first raster in the correct pre-processing resolution, which you determined, in this case 50 meter, you can use this. And you should also always try to use the snap to raster function, because then really the GIS software normally perfectly aligns the raster grade. So the center points of each raster cell are perfectly matching each other, which will prevent you again from some post-processing steps that would be necessary then. So we convert all that stuff the same way. In this case, I created it already here. So I did all the steps, clip the polygon, convert it to TIFF, convert it to ASCII, use the MIC0 toolbox and convert it to a raster. I check again just to be sure if the values are correct. So I expect here grid values from 1 to 15. And it looks good. They are here. Take the correct item type. In this case, it's grid codes. If you don't know what is the correct grid code, you can also, give me a second, always create a dummy raster in here. This will always create an empty raster. Go to items and you see which item type is requested. Once this is done, let me check. I think I closed the new model I just created with you. 1 second. Here we are. Okay. These steps were not saved. So I jump directly to this step. Again, you have here different options regarding the land use. You can select the land use or define it based on the combination of a grid code, with what we will do now, together with so-called evapotranspiration files. I will show you in a second what this means. Or you define them completely individually. Then Mike-Shi is expecting you to insert rasters. Raster for each parameter that you need for the evapotranspiration. And they are the leaf area index, the root depth, the crop coefficient, canopy interception, and the deficit for the ET reduction. If you use the two-layer method, if you use the Richards equation, what we want to do, you need these 4 parameters. You will see more explanation in the online help. So we go back. We want to go for the grid code approach. We don't want to use only one value with a constant temporal distribution. No, we want to go for the sub areas. So it's asking me again for this DFS2 grid. And navigate to the prepared land use, which I just showed to you. And I get all the grid code values here. And now Mike-Shi asks me to insert for every grid code one time series for the leaf area index or for the root depth, because we have a temporal variation. Alternatively, you can use ETV files. These ETV files you probably don't have at hand when you start, but we will offer in January the download of a so-called default database that we use. How does that look like? This is a separate file format that contains leaf area index and root depth distributions that we developed over the years in many projects and based on literature research for exactly these 15 categories that we use in our standard projects. So what you can see here, these are less than 15 because you take some of them, like water, no vegetation, you can apply for buildings, streets, residential area, and lakes. And for each, I'll probably go to the forest. We differentiate between coniferous, deciduous, and mixed. You get a distribution for the leaf area index and the root millimeters. So I go to my model, create here a new line, and directly navigate again to this ETV file. Grid code 1 I know now are my lakes. So I take this one, and then I go through all the steps. In this model setup, I have done it already. You should always check here recycling the entire scheme. Otherwise, it will complain that the time series is only here for 1 year. And doing it like that, you will get the typical transient distribution here in this window. And then you're ready to go with your land use. For the overland flow, it's even easier, right? You have converted again the rasters, and you can directly link then the Manning raster for the roughness. Here values from 0 to 30, again based on literature research over the years, and also the subsurface sealing. So here you can directly see the urbanized areas where we want to prevent too much infiltration because we expect stronger direct runoff. There are other modules available, for example, the ponded drainage, that helps you to simulate also the water that is taken out by the canals, by the sewer systems and so on, in a more indirect way on a cell base. And now we come to the last part of our module, which is unfortunately also the most complex one. And these are the soils for the unsaturated zone. So what is always a little bit a challenge is to find good data. For the land use, it's normally more easy because you can create this based on satellite images. But for soils, you normally have different parts, kinds of soil maps. They have a different resolution, maybe the scale 1 to 50,000, 1 to 200,000. In this case here for Germany, we use for this model, testing model here, the one with the resolution 1 to 200,000. And what you see here is a quite confusing legend and some numbers, but you can use these as identifier. And especially for Germany, we have already such a lookup table. And we have quite extensive data on that. I will probably not have enough time today. But what we do then again, within your root installation of MikeShe, you will get a so-called standardized soil database based on Rosetta, the Rosetta approach. And this aligns with the globally agreed soil categories of clay, sand, and silt with separate in-between levels or mixture rates. And what you do again in Excel, you see here the legend that I used in GIS. And using ChatGPT, I can give that the typical UNSODA or USDA Rosetta categories, loamy sand, sand, and so on. For each one, I again determine myself a soil ID. This is random. This is up to you. This you will use as a numerical identifier for your soil ID. I export this Excel again to a text file, join it to my soil map. You can see it here. So I have here my original soil ID, soil type. This is the German classification. Maybe you have a national one. This is the bulk density. We have here levels from 1 to 4, and the classification I would like to use for the soil, and one as text and one as an integer number. So I convert this polygon shapefile I have here again into a raster with grid codes and converted this feature into a raster with 50-meter cell resolution, following the steps I showed initially, and then convert it into an ASCII raster that is here. I convert the ASCII raster again to a DFS2, and use it here as my input. It works exactly the same way like the land use. So I have now the predefined grid codes from 1 to 25. Not continuous. This is now all the color symbology. Not all of them are within my active model domain. And I start with the first. What you normally do here, let's start from scratch. Here. It creates me again a sub-dialog for every grid code that he identifies. I recommend you to change the naming here to a more value that is more intuitive for you, showing that there is loamy sand, sand, silt, or whatever. And then you can, as long as you're using here the Richards or the gravity flow, which are the fully differentiated ones, the fully discretized ones, you can use really for each depth column a different value. So this is like in centimeters. Let's say for the first 20 centimeters, I want to use this soil column. For the next, I want to use this. And you normally go until 2 meters below topography. And for each of these, you can use the default soil database that you find within your root directory, within the pre-installed examples. Here. And this is such a so-called UZS file. This UZS file contains all the parameters for different approaches to solve the modified Van Genuchten or other approaches. So you see here different soil types. If I go to the clay, you always have values for the retention curve here and the hydraulic conductivity. This is quite complex stuff and is probably worth a separate webinar later that year, but you don't have to deal with that at the moment because you can use these predefined values. And then you link it exactly the same like you use the ETV file. So I close that one again. And I chose here the first value. For example, I want to stay with clay loam, start with clay loam in the first level. And then maybe there comes a sandy layer. And you continue to the very end. It's important that you choose here a length that is quite deep because it must overlap with the groundwater model later if you want to use the groundwater model itself, what we don't do today. So for the moment, it should be okay to use only the two. Cell heat, the top should be discretized in smaller steps, and then you can get more coarser. So for example, 0.1 in the first, then 0.2, 0.5, and so on. The maximum length that you have defined here should match this one. Otherwise, Mike Xi will complain that you have numerical layers within the unsaturated zone module, which have no parametrization right now. When you do all that steps, it could look like here. So here I have again my soil columns. You see some of them are even outside of my model domain and therefore not relevant. In this case, I neglected here a vertical discretization for the sake of simplicity. And today I will not have enough time, but the same way using GIS procedures, you can of course derive also a mean groundwater table as spatially distributed but temporally constant DFS2 grid and use this as lower boundary. And then you can basically press run. This time, next to the gridded output to the rasters, you can also define here any detailed water movement WM time series for any item. So for example, for the actual evapotranspiration, you can differentiate even between transpiration and soil evaporation. You can use here this cross to place. You can change the numbers. You can define if it should be a new plot or not. And you can even include observation data. But this part I will show you in the next webinar. And then you press run. It runs a few hours. And then we end up with this nice grid. By the way, if you're a FeeFlow user and you need recharge, there's a direct DFS2 import function within FeeFlow. If you are a ModFlow user and you want to use this one only as input for your ModFlow groundwater model, we offer also a for free conversion tool. You can request it from me or via the DHI customer care support. If you write an email to mike@dhigroup.com, which converts your transient DFS2 rasters directly into the recharge input files that you would need for a ModFlow model. Of course, you can also run the full 3D groundwater model within this model. Then the recharge model, what I showed you today, and the groundwater model would have a bilateral coupling. What this means, I will show you probably in January. And that's it from my side from today. I tell you, there are a lot of steps and you will have to consider a lot. But my commitment and my offer is, if you follow this webinar series and you carefully look into the online manual, you will learn not only how to work with Mike Xi, but how to do groundwater models, how to work with GIS, how to work with, how to use all the typical procedures you need to take into consideration if you want to do numerical modeling for any case within the water management. So thanks a lot for your attention.